concrete is really strong in compression, but we typically reinforce it with rebar, right? And this one I did pre-tension, so this cable running through here is tensioned up already. We have the option of putting that in the center, the bottom, the top, or maybe all the way around. All the way around is probably going to be the strongest. But if you only have one option, what do you think is the strongest positioning?
Bottom. Where the tension is.
Anybody have anything different? Center. Where is it going to be if you got a floor ceiling assembly, where is it? Or a concrete slab, where is it? When you see like post tension nuts.
Center.
They're always in the center, right? Always. So what we're going to do is we're going to just test this one. I've never tested it before. Let's put it on the bottom first and sit it on here and put it in our testing apparatus. And we'll start adding weight and see when this sucker breaks, okay? And we're trying to do a static load, so don't drop it on there because we can't measure what that is. Do you understand that, Kaiser? The last alert I had do that with all their weight. Now I don't know what the load was.
No, Bo, no! I thought you said go, Bo, go!
All right. You ready for it?
I'm ready. I thought I was trying to warn you. You wanted me to break it. I wanted to test when it breaks.
Anybody have an idea about how much it holds?
Hold it.
Anybody good at math?
That's 115.
Or is it 25?
Here's some concrete. I'm not sure if that's the wood or concrete though.
140, 185. 230.
See if you can get on there without jumping there. So let's put your body on there and rotate up on there. Yeah, get your feet up.
How much you weigh?
Weigh one with my clothes on, probably about 200. Get on too.
Yeah, get on there. Get on there.
This is not going to be good.
Ride 'em like a pony.
Where's the pictures at?
Oh, it's cracking.
It's cracking.
Was that your back or was that?
No.
No, it cracked. It didn't blow out, but it cracked. What do we get
So the
to?
concrete failed, but the rebar is holding it.
Call it
230.
630,
230 plus
200, 200.
630. That sucker handle, it's still pretty dang solid. But it cracked. It cracked, but it didn't fail. So the cables did pretty good. Just looking at it, if we put it this way, you can't even hold it up right. You see how the force suspends it from the bottom? Is that kind of help? And I know you can see it, but we'll just do it with this so you can see that as well. So if it's bending down where the top is pushing together, right, kind of crinkling up, and the bottom is stretching, so that's the tension, which y'all predicted. Most classes don't, but some of y'all understand these things a little bit better.
Cliff has a lot of Sawyer experience. I think that's.
So typically the top in this configuration is going to be in compression, the bottom's in tension, and the middle is a neutral plane. So reinforcement in the middle is not really doing anything because there's no force applied upward around because there's opposite forces on each side of it. So there's nothing going on there. So the only thing the rebar does in the middle is just keep the pieces after they crack from separating. That's really all it's doing. It's not resisting any force. So if this is that cable, can you push a rope? No, you can't push a rope. So it's only good in one direction, right? Pulling. So even if this was rebarred, it's stiff. Like all these guys over here that we've broken, if we're pushing on it, it's just going to bend. However, if we try to pull it, it's pretty strong. So being at the top is pushing together, so it's not providing any resistance to the forces. But being on the bottom, it's in tension, so it does provide force. So just by moving it within the beam, goes from no added strength to a lot of added strength. When we got this guy and we had flipped it over, they typically fail with just 145-pound plate. Sometimes just 125-pound plate. So a huge difference between 25 or 45 pounds versus hundreds of pounds of strength. That's in this one orientation, but if say this is a beam on several posts or walls or whatever it is, and you have loads all the way across this thing, it's gonna be tension down here, but right here over the post, if I'm pushing down on both sides, look at it, it does the opposite, right? So now your tension's on the top, compression's on the bottom. So in this orientation, these trusses, you can look at them, so they're pinned on two ends, they span across an open area so you can read the force of this entire thing and know that bottom's in tension, top's in compression. But if it's something that kept going, that would alternate, so you would need the same amount of strength or reinforcement on top and bottom. That makes sense? So the biggest takeaway is, without the steel reinforcement, concrete is super weak. If it's in compression, it's strong. So one other example is we build a nice foundation of good solid soil. We put rock, crushed rock on there, limestone or whatever we use to make a good bed. We roll that with a roller, everything's packed and solid, several feet deep, then we pour a concrete slab on there. We don't even have to put rebar in there. Once that dries, we can drive an 80,000 pound truck across it and it doesn't break, because the entire time that concrete's in compression, right? However, if that soil washes away and you have like a pocket, gophers get under there, and then it washes out and you have, see the center bottom drawing? There's a drawing over right there, you have concrete, and then you drive across that section right there, it's gonna blow out immediately, right? Because it has virtually no strength in tension, because you're now putting that section, the bottom of that concrete slab in tension.
In order to put our understanding of tension and compression into practice, this is where it matters. When you have an unreinforced masonry wall, such as cinder blocks that don't have rebar, or a brick wall, which is only held together by masonry, it acts like concrete in that it is strong in compression, but it is super weak in tension. So as long as that wall is in compression with just a straight vertical load on it, it's still a strong wall. But as soon as structural members start to shift, such as in this picture where you see the timbers are burning in half and they start to sag and move the walls, that puts a portion of that wall into tension, and therefore it's very likely a high probability of collapse, inward, outward, curtain wall, whatever type of collapse. So we need to during a time in which the fire has consumed a lot of the building, we know that there's involvement within those structural members. We need to establish collapse zones and enforce them. It's probably a defensive fire at that point, and that's oftentimes when firefighters have lost their lives, which is an unacceptable risk. So cinder blocks, we don't know if they have rebar in them or not, so we should presume that it is unreinforced masonry until proven otherwise. We probably don't have time to go inspect it. So let's just presume that cinder blocks and brick walls have a high probability of failure, and during a significant fire, we will avoid them to prevent injury and catastrophic death of our friends.